Okay, how you guys doing? Good. Cool. Very cool. So today we're going to talk about Class C amplifiers. So far we've talked about Class A amplifiers, Class B, Class AB, and we're going to move on to Class C tonight. First we're going to start with a review of Class B and Class AB, like we talked about last time. And then we're going to go on to Class C. We'll see what they are. They're amplifiers that work for an extremely narrow band of frequencies. Okay, so our other amplifiers have been really good at amplifying a wide range of frequencies. And this is very useful when we're doing things like amplifying our voice, because our voice can go, for a wide range. Music is over a wide range of frequencies. Human hearing usually ranges from about 20 hertz to 20 kilohertz. So that's, 1,000-fold difference between the lowest range and the highest range, and we want to be able to amplify all of those frequencies evenly. So that's what Class A and Class AB amplifiers have done for us. But we'll see that Class C amplifiers only work for a very narrow band. We'll see one of the reasons that we use them is that they're very efficient. All right? So they only work for a very narrow band, but in that band they're very, very good. The Class A and Class B amplifiers have been not great. These are very, very efficient, these Class C amplifiers. We'll talk about a couple of applications for them. We'll go into how they work, and we'll see that they can actually be used as frequency multipliers. So if you have a 1 megahertz frequency, for instance, you can use a Class C amplifier to create a 2 megahertz frequency. So we'll see how that works. Okay. Then we'll do a preview of today's lab. For the lab, no surprise, you're going to be able to actually make a Class C amplifier. So you'll use it, you'll calculate the frequency that it's going to amplify, and then you'll also use it to amplify and actually use it as a frequency multiplier. So you'll put in a low frequency signal and see that you can get out a higher frequency signal. Okay? Any questions before we get started? All right. Cool. So let's start with a review. So last time we talked about Class B amplifiers and Class AB amplifiers. So let me draw those up on the board. So last time I drew the amplifier just the way that it's drawn in your book, and that was a little bit confusing. The amplifier that's in your book is actually a little bit more complicated than a standard Class B amplifier. The one in your book is a Class B amplifier that only has a positive power supply. Okay? Most Class B amplifiers have a positive and a negative power supply. And if you draw it that way, it's actually a little bit easier to understand what's going on. So let me do that. So you've got your input signal here, you've got a capacitor. You've got a resistor. You've got your positive supply up there. Another resistor. And now down here, we actually have a negative supply. Okay? This is what you would do if you had both a positive and negative supply to drive this amplifier. You would still have the two transistors like we had before. The emitters would be connected. And then the output would be right there. This would be our load resistor, So this is sort of the generic Class B amplifier. It has both a positive and a negative power supply. So let's see how this works. We've got our input signal here. I'll do that in green. So this is a nice sine wave. So when the input signal gets a little bit positive, what happens is that I'm sorry. I left off the connection to the bases here. So when the input signal gets a little bit positive, this part of the voltage gets a little bit positive also. So that allows current to flow up through this, from this base down through the emitter here, and flow to ground through the load. Okay. And when you have a small amount of current flowing that way, that allows a large amount of current to flow down this way. So this is a lot of current here. Okay, so a small positive voltage in allows a small current to flow from the base through the emitter of this top transistor, and it allows a large amount of current to flow from the collector through the emitter of this transistor. Okay, this bottom transistor is reverse biased, right? The diode is pointing inward,
which is a PNP.
right? So it's a PNP. So this part of the this base is slightly positive, just like this one is slightly positive. So it's reverse biased, so no current flows through that transistor there. Okay? So far, so good? All right. So then let's look at what happens when we have a negative voltage on our input. When we've got a negative voltage here, we have a negative there, and a slightly negative voltage in both of those places. So this allows a small amount of current to flow from the ground through here and back to our input. And that small amount of current flowing in that direction allows a large amount of current to flow from the ground down through here, down to our negative voltage. So we have a whole lot of current flowing in this direction. Okay, small amount of current flowing this way, large amount of current flowing from there down to the negative voltage. Okay. Does that make sense? So this is really a current amplifying circuit. It just takes a very small amount of current coming from the input, and it allows a large amount of current to flow through our load, either down through this top transistor to the load, or up through the load and down to the negative voltage through the bottom transistor there. Okay. Questions about that so far? Okay, so these transistors don't turn on immediately, right? In order for these transistors to turn on, we need to have some voltage at the base. And that base voltage needs to be about 0.7 volts, right? Because there's essentially a diode inside of that transistor, so you need about 0.7 volts to overcome the diode and allow current to pass through. So what happens is that I'm running out of colors here, so I'll use blue for the output also. So so the output doesn't turn on immediately. It turns on when this voltage gets to 0.7 volts. So if you were to look at this and you were to go up here and figure out exactly when this output voltage turned on, it would be when the input voltage reached 0.7 volts. Okay, and then it turns off again as soon as the input voltage is below 0.7 volts. Okay, so what you get is this distortion, and it's most noticeable right where the signal crosses 0 volts. You get these dead zones around 0 volts. We call that crossover distortion. Okay, so you see the same thing in both the positive and the negative cases. In the transistors don't turn on until the voltage is at least 0.7 volts in the positive direction, or minus 0.7 volts in the negative direction. So the output is off until the input is at least 0.7 volts. Any questions about that? Okay, so the DC load line for these types of circuits looks like this. This is the current through the collector, and then this is the voltage between the collector and the emitter. So the Q point for a Class B amplifier is right here. That is when there is no voltage, or when there's no current flowing, there's no, or when there is no input voltage, there's no current flowing through the system. Okay? So when the input is quiet, there's no current that's flowing through our circuit. So that means that this is reasonably efficient because it's not wasting current when there's no signal coming in. Okay. But you still have this crossover distortion, which is not good, right? If you were to play an audio signal through this type of circuit, it would sound really weird. It would be bad. So we don't like this crossover distortion. So what we need to do is we need to find a way to get rid of this and still try and retain the efficiency of the Class B amplifier. We're trying to get the best of both worlds, right? That nice looking signal that comes from a Class A amplifier with most of the efficiency of a Class B amplifier. So the way that we do this is that we insert two diodes. So I'm going to reuse this picture. And I'm going to turn this into a Class AB amplifier. And the way that we do that is we really just insert a diode there and a diode there. And instead of having just one capacitor, we have capacitor up there and capacitor down here. Okay. So what these diodes do is that we needed a 0.7 volt difference in order to turn this transistor on. So this diode gives us that 0.7 volts. Even when you have no signal coming in, you have a little bit of current flowing through here. And so this point is 0.7 volts above our input. So this transistor is always right on the verge of turning on. Whereas before we needed the input to go up by 0.7 volts in order to get that offset to make the transistor turn on. Now, this diode already gives us that 0.7 volts, so the transistor is always right on the verge of turning on. So any small increase in our input will allow this transistor to turn on. So that gets rid of this crossover distortion. Okay? Questions about that? So that means that the Q point for a Class AB amplifier is right here. So when no signal is coming in, there's just a small amount of current flowing through our circuit, because it takes a small amount of current flowing through these diodes to activate them. So there's just a small amount of current, but it's not, half the current like it was for a Class A amplifier. So we still get most of the efficiency of the Class B amplifier, while at the same time eliminating the crossover distortion and getting the nice signal reproduction that we see in Class A amplifiers. So, questions about that? Okay, cool. So that was what I wanted to say about Class B and Class AB amplifiers. So let's go on to our lecture and talk about Class C amplifiers. All right. So, what are Class C amplifiers? Like I mentioned at the beginning of the lecture, Class C amplifiers are amplifiers that work over a very narrow range of frequencies. So they don't operate over a wide range like Class A and Class B amplifiers. They operate in a very, very narrow range. We use them because they're very efficient. So even though they only work in a very narrow band, they're very, very good at amplifying frequencies in that narrow band. So as far as applications for these types of amplifiers, I think somebody mentioned earlier when we discussed these a few lectures ago, these are very good for radios, okay? Because when you are looking at a radio frequency, oftentimes you want to amplify only a very narrow band, right? You want to amplify the station that you want to listen to. You don't want to amplify all the stations that are next door. So Class C amplifiers do just that. They're very, very efficient at amplifying a narrow band like the station that you want, and they actually will not amplify the stations next door. So it's sort of a 2-for-1. It's good at what you want, and it eliminates what you don't want. So let's talk a little bit about how they work. Basically, the heart of a Class C amplifier is a resonant circuit called a tank circuit. A tank circuit looks like this. You've got an inductor and a capacitor in parallel. And what happens with a tank circuit is that it resonates at a particular frequency. Okay? So, to understand why that is, to understand how tank circuits work, we have to understand a little bit about capacitors and a little bit about inductors. Okay? So, let's talk a little bit about capacitors. You guys probably remember a little bit about capacitors from ET302, right? So the essence of a capacitor is just two plates of metal that are close to each other and separated by a small insulating layer. So what happens with capacitors is that if you put a bunch of negative charges on one side of the capacitor, then this repels the negative charges from the other side, or you could think of it as attracting positive charges to the other side. So you can put a voltage on a capacitor and it will charge the capacitor up like this, and then you can remove the voltage and the capacitor will retain its charge. But if you attach a wire from one side of the capacitor to the other side, then all of these negative charges are going to be attracted to the positive charges. So all of the negative charges are going to flow out through the wire and go around to the other side, and they're going to cancel out the positive charges. So you end up with the same charge on both sides, right? Or you could say that neither side is charged. So you can charge them up as long as you don't have any wire from one side to the other, and then you can discharge them by connecting a wire from one side to the other. Okay? So that's a little bit about capacitors. Inductors are a little bit trickier. To understand inductors, you have to understand a little bit about what happens when wires are next to each other. Basically, if you've got two wires next to each other and you push some electricity down one wire, it actually drags along a little bit of electricity from the wire next door. Okay? So the electricity flowing through this first wire sort of pulls on some of the electrons from this other wire and causes those electrons to move as well. So if you hook up a current in this one wire and then you try and measure the current in the other wire, you could actually measure current flowing through the other wire even though you don't have it connected to a voltage source or anything like that. Just the current flowing through this wire causes some current to move in the wire next door. Okay? It sort of drags it along. And that actually makes it harder to start the current flowing in this wire because it has to drag along this other wire. So the more wires you have next to each other, the more this effect gets magnified because you've got this current flowing through the first wire, and then that drags along a little bit of current from the next wire. But then that current has to drag along a little bit of current from the next wire, and so on. So they just, so the more wires you have next to each other, the harder it is to get the current flowing in one of them because it has to drag along all this current from all its neighbors. All right? And similarly, once you have the current flowing through all of these wires, it's hard to make it stop. Because if you try to make it stop here, all these other wires already have current going through them. So they're going to try and pull this current through this middle wire and keep it going. So basically, when you have a bunch of wires next to each other, it's hard to get the current to start going. And then once it's going, it's hard to get it to stop. All right? So basically, the current just wants to keep doing whatever it's doing. If it's stopped, it wants to stay stopped. If it's going, it wants to stay going. All right? And this is essentially what's happening inside of inductors. An inductor is a big coil of wire. So really, it's just a big coil of wire. If you were to look at this coil of wire, what you would see is, if you were to saw it in half and look at it, what you would see looking end on is a bunch of wires stacked on top of each other. So these are really wires that are lying right next to each other, okay? And sometimes, inductors have multiple layers of these wires, so they might be like this. So you've got all these wires lying right next to each other. So the effect that I was talking about a minute ago is very much happening inside of inductors. When you start a small amount of current flowing through, say the wire's coming in through the top here, and then it's going down into this first coil, and then it's coming around. So you're trying to push electricity into this first wire, but then that has to drag some electricity through this other wire, which has to drag some electricity through this one, which has to drag through this one, and so on down the line, right? And all of these. So when you push a little bit of electricity through this first one, it has to sort of drag along all of its neighbors in this inductor. So when you try and start electricity moving through an inductor, it's hard to do, right? Because it's getting dragged back by all of these other wires which don't have electricity going through them yet. And similarly, when the electricity is moving through the inductor, it wants to keep moving through the inductor. Okay? So that's a little bit about inductors and capacitors, and I think that'll help us understand a little bit more about this tank circuit and how that works. Okay? So let's examine the tank circuit here for a minute. So what happens with the tank circuit is that you start off with the capacitor all charged up. You've got a bunch of negative charges up here, a bunch of electrons up here on this side of the capacitor. So you've got a bunch of positive charges on the bottom of the capacitor. Okay? But you've got this inductor going from one side of the capacitor to the other. And really the inductor is like a long piece of wire. So this capacitor has a path from the negative charge around to the positive charge. So this capacitor is going to try and discharge itself, right? So these negative charges start flowing along here, and they start going through the inductor. and they have a little bit of a hard time to get started, like we talked about a minute ago, but they get moving and they start coming around here, and pretty soon they're moving pretty fast, and they start to cancel out all of these charges, the positive charges, on the opposite side of the capacitor. So if we draw this like a cartoon and look at the situation, a moment later, you would see something like this. A moment later, all of the negative charges, the last negative charge is now flowing through our inductor, and it's canceling out the last positive charge over on this side of the capacitor. So the capacitor is just about leveled out. In fact, our last charge flowed through, and everything is completely even on both sides of this capacitor now. But this current has been flowing for a while, so now it's actually flowing really fast through this inductor. And we know that when the current is flowing through the inductor really fast, a whole lot of it going through there, it wants to keep on moving. So what this inductor does is that it actually keeps on sucking more charges from this capacitor. Even though the capacitor is perfectly happy now, the inductor wants to keep going. So it keeps on sucking more charges off. So what happens is that a moment later, the tank circuit looks like this. You've got your inductor over here, you've got your capacitor, and the inductor has sucked off even more of these charges. So now you've had more electrons flowing, so now this side gets a positive charge. And since the electrons are still flowing to the other side ends up with a negative charge. Okay? And this can't go on forever, because this capacitor pushes back more and more the more it gets charged up, right? So it is pushing back against this flow. So eventually the capacitor causes the flow to stop. Okay? But at that point, the capacitor is charged up in the opposite direction of where we were at the beginning. So now the capacitor has a bunch of negative charges on the bottom, a bunch of positive charges on the top, and now it wants to discharge itself in the opposite direction. Okay? So a moment after this, what happens is that you're back to flowing in the opposite direction. So the charges are flowing off of the capacitor, but this time they're going the other way. So they're going from here and moving around like that. Okay, so it just goes like that, and so now you've got a lot of charges that are flowing. The capacitor evens out, but the inductor wants to keep going. So a moment later, it keeps on sucking these charges off, and you end up back where you started off, with a bunch of negative charges on the top and positive charges on the bottom. Okay, so it just keeps on going back and forth like this. You get a bunch of charges up here, they get sucked around, and they end up down there, and then they get sucked around the opposite way, and then they end up back on the top, and so on and so forth. So it goes back and forth and back and forth. Okay? So that's how a tank circuit works. Any questions about that? Okay. So the tank circuit actually has a resonant frequency. Okay? This oscillation back and forth happens at a very predictable rate. So you can actually calculate that frequency. So the frequency of oscillation is 1 over 2 pi times the square root of LTCT. This is the inductor in the tank circuit and the capacitor in the tank circuit. Okay. So that's the frequency of oscillation. So if you know what inductor value you have and what capacitor value you have, you can calculate this frequency. Or alternatively, if you know what frequency you want this to resonate at, you can choose an inductor and a capacitor to make it resonate at that particular frequency. Any questions about that? Okay, so this is really the heart of our Class C amplifier, but it's not the whole thing. Okay? If you just had a tank circuit like this by itself, what would happen is that you would have this oscillation going back and forth, but it's not 100% efficient, right? Each time it goes around, it loses a little bit of energy, right? These wires have a little bit of resistance, so a little bit of the energy gets turned into heat, and eventually it would oscillate down and basically go away. So what a Class C amplifier does is it has a little bit of extra boost, basically. Okay? So what happens is that the Class C amplifier has a way to add a few extra positive charges to this circuit. So basically, every time the circuit gets to this point in its oscillation, the Class C amplifier just adds on a few extra positive charges over here, which creates a few extra negative charges over there. So it just gives it a little bit of push. Okay? You can kind of think of this like pushing somebody on a swing in a playground. So if you let them swing by themselves, they would swing for a while and eventually they would just peter out and stop. But if you let them swing and you give them just a little bit of a push right at the top of their swing, then that little push is enough to keep them going, you know, indefinitely, as long as you just keep giving them a little tiny push each time. So that's what the tank circuit does, or what the Class C amplifier does. It gives this tank circuit just a little bit of push by adding just a few extra charges every time, and so it keeps the oscillation going that way. So just like on the swing in the park, it's important to add these electrons at just the right time, or add these charges at just the right time. Imagine what would happen if you tried to push somebody right at the bottom of their swing, right? You would run straight into them, and you wouldn't be adding the energy. So you have to push them at just the right time in order to get it to work. If you push it at the wrong time, it does not work. So another way to think about that is that this amplifies those pushes that happen at just the right time. So if you have an incoming sine wave that's at just the right frequency, this circuit will absorb those little pushes and amplify them. If your sine wave coming in is at a different frequency, then it will not cause this tank circuit to resonate, and so it will not amplify, the tank circuit will not amplify your incoming signal. Okay. So the way that the rest of the circuit is constructed, where did I put the eraser? Here we go. The way that the rest of the circuit is constructed is that we've got our positive voltage supply up there. We've got a transistor down here. we got a negative 1 volt signal there. And then we've got our input over here. And then our output is coming from this point. So if we had no input signal, then this voltage right here would be -1 volt. So our input signal, and this voltage has to go up to about 1.7 volts, or I'm sorry, 1.7 volts greater than -1. It has to go up to 0.7 volts greater than 0 in order to turn our circuit on. So we can adjust our input voltage here until we're just getting a little tiny push right at this point in our circuit, at the base. So we should see just a little tiny push at our base, and then that will cause our circuit to resonate. If we have our input signal too large, that will actually throw off the resonance. And if we have it too small, it's not going to give it any kind of push, so it will not work. So we need to adjust our input signal until it's just big enough to give our tank circuit a small push. Okay. So this is the way that our signal, or our Class C amplifier is constructed. So when our input turns on, that allows current to flow down through here. So that just gives it a little bit of push at just the right time in the cycle. Okay. So any questions about that? Okay, so that's a little bit about how Class C amplifiers work. So it turns out that you can actually use these amplifiers as frequency multipliers. Okay, so let's talk about that. Basically, this is like if you went to the park and you were pushing somebody on the swing, but you only push them every other time, right? So maybe you push them 10 times a minute, but the swing is going, bless you, back and forth 20 times every minute, right? So you would push them, and they would swing once, and then they would swing back and you would miss, and then you would swing and you would push them again. So if we looked at our input signal, might be something like this. So what we could do is we could pick our tank circuit, or so that it resonated at twice the frequency of our input signal. Or conversely, we could pick our input signal so that it resonated, so that it was half of the resonant frequency of our tank circuit. So our tank circuit would look something like this. It would have a big peak here, and then it would go down a little bit, and then it would get another push. So the peak would get bigger, and then it would go down a little bit, and then it would get another push. So it would be something like this. This would be the output signal from our circuit. So the frequency is twice as high as the frequency of our input signal. So this would be a 2 times multiplication of our input frequency. You could also pick at 3 times multiplication, right? If you did that, I'm not sure if I'm going to be able to do this very well, but we'll see. So it would be something like this. You would get a big push for every third cycle of your signal. So the output is not going to be a perfect sine wave, but it will be at a higher frequency than your input. So you can take a lower frequency input and create a high frequency output. Okay. Any questions about that? Okay. So I said that the tank circuit, or the Class C amplifier has a narrow band of frequencies for which it will amplify, but I didn't really define how we can tell what that band of frequencies is. Okay, so what we can do is we can look at the maximum voltage that we get out of our circuit, and then we can see how that voltage decreases as we move on either side of our resonant frequency. Okay, so we could actually draw this on a graph, right? So we could look at the peak-to-peak output voltage, for instance, versus the frequency. So we could say maybe at the very best frequency here, at our resonant frequency, we get 10 volts peak to peak, okay? But then if we start measuring, if we put frequencies in that are on either side of our resonant frequency, the circuit's not going to work as well, right? It'll still amplify, but not as well. So it'll be a pretty steep drop off, right? So it might look something like that. So it works best at this resonant frequency, and then it works worse and worse the farther we get away from this resonant frequency. So we can define the band where this circuit works. We can say that the band is everywhere that is. We can say the lower cutoff is where the output is 0.707 times our peak voltage. Okay, so if we had a maximum voltage of 10 volts, then the lower cutoff would be wherever the output dropped to 0.707 times that, and the upper cutoff might also be wherever the output dropped to 0.707 times our maximum. So we can find the minimum frequency and the maximum frequency that way. Any questions about that? So our resonant frequency is right in the middle, our minimum frequency is the lowest, and the maximum frequency is the highest frequency that we can get, while still getting an output of at least 0.707 times our max. Okay, so that's all I wanted to say about Class C amplifiers and frequency multipliers. For your lab, you're going to build a Class C amplifier. You're going to use this formula to calculate its resonant frequency. And then you're going to put that frequency into your function generator, and you're going to create a sine wave at that frequency. You are going to turn the amplitude down until the output resonates. So you're going to look at the input and the output. You should see the output is a nice, clean sine wave. If it's looking too distorted, you need to turn the input down. If it's not there, then you need to turn the input up a little bit. So you want to adjust the input until it's just getting the output to resonate. Okay? And then you're going to change the frequency up and down a little bit, right? So you're going to calculate the center frequency, and then you're going to change it a little bit on your on your function generator, because chances are the calculated frequency is not going to be exactly where the resonant frequency actually is. You have small variations in the inductor or the capacitor, and that can throw off your actual frequency. So you're going to change that around until you find the maximum output voltage. So you're going to record the frequency that gives you the maximum output voltage, and then also the voltage that you get at that point. And then the next thing you're going to do is you're going to calculate the frequency range. So you're going to find the minimum frequency and the maximum frequency. You're just going to tune the function generator around until the output drops down to 0.707 times the max. And you're going to record the minimum and maximum frequencies there. You're going to sketch the input and output waves for this. That's actually going to be at the resonant frequency. Okay, so when you're at your resonant frequency, you're going to sketch your inputs and outputs. And then you're going to use this circuit as a frequency multiplier. So you're going to use the same circuit, but you're going to set your frequency at half of the resonant frequency. And then you're going to look at your input and output, okay? And then you're going to do the same thing, again, same circuit, but you're going to set your resonant frequency at a third of your input frequency at a third of the resonant frequency. So you should be able to get a 2 times multiplier and a 3 times multiplier out of just this one circuit. So you're only going to build the one circuit tonight, but you're going to use it in a couple of different ways. Yeah?
Briefly cover how to actually do that calculation.
Sure. So let's say that you had an inductor that was say 10 millihenries, and the capacitor is 0.1 microfarads. So then you would just plug in those numbers. You would say the frequency is 1 divided by 2 pi square root, and you would have to convert these into raw units. So 10 millihenries would be 0.01 henries times 0.1 microfarads would be 0.0000001 farads. So you would multiply those together, you would take the square root, you would multiply by 2 pi, you do 1 over that, and then you get your frequency. So I don't have a calculator with me, but those are the steps. Does that make sense? Kind of?
Yeah.
Okay. Other questions? Okay. All right, so then I will take attendance and I'll let you take a break.
you.